Hello.
Hello.
Hi, Tyler. Good evening.
Uh,
How's everything going on?
Everything's good. How about you?
Okay, perfect. Had we covered something about momentum in the previous class?
No. I
Nothing?
think we just no. This is the first class. I think we're doing momentum.
Okay. So, do you think that you have done the theory and should we jump to numericals or would we cover some basic theory? What do you think?
Wait, can you repeat that?
Should we cover some basic theory or you have done the theory and we can directly jump to the questions?
I would want. Let's just go over the basics. Like,
Okay, perfect.
I just wanna review it.
So, do you know what is momentum actually?
Uh, like how much force?
No, it's not a
No.
measure of force. Momentum is actually a vector. Okay.
Oh, yeah. Okay.
And the direction of momentum vector is the direction of the velocity vector. Right. But
Mm-hmm.
both of them are not same. The momentum vector is product of mass and velocity vector. Okay. Mass is a scalar
Mm-hmm.
thing, right? And it is product of both of them. Like you can see here, linear momentum. Okay, so what is linear momentum? It is defined as the product of system's mass. Okay, so what is your system we are choosing? Okay, so that system mass multiplied by velocity of that. Remember, it's not speed, right? Momentum
Mm-hmm.
is product of mass and velocity, not mass and speed. Okay, so if there is
Yeah.
mass and velocity, then the sign of the velocity there is important, right? Is that right?
Mm-hmm.
If I say
Yes.
the momentum is 2 and if I say that my momentum is negative of 2, both are different, right? Is that right?
Mm-hmm. Yeah.
Right? Because there is mass and velocity, right? And velocity is a vector quantity. For that, sign matters. Is that right? Okay.
Yes.
Yes. So since it is a product of a scalar and vector quantity, so momentum is itself also a vector quantity. Okay. So this is the formula for momentum of any body. Okay. Now the thing is that okay, there is a 110 kg football, okay, that is running at 8 meters per second. So what will be the momentum of this football? Can you tell me?
Uh, 110 kilograms times 8 meters per second.
Perfect, very good. So its unit will be kg meters per second in SI units. Is that right?
Mm-hmm.
Okay.
Yes.
So momentum of the ball is, you got here, that is 880 kg meters per second, right? Now, there is another, compare the player's momentum. Now, this is the momentum of the ball, right? Now we have to compare this with the momentum of the, uh, oh, that is the momentum of the football player. Now we have to compare this with the momentum of the football, right? So what is the mass of the football? Is that 0.41 kg?
Mm-hmm.
And the speed is 25 meters per second. So the speed of the football is higher than the speed of the player. Is that right? Is that right?
Yes.
So let's calculate the momentum of the ball. What will be that? Can you tell me?
Uh, 0.41 kilograms times 25 meters per second.
Yes. So what you are getting? Let's check. So when you do the product of both of them, you will get the momentum of the ball is 10.3 kg meters per second, right?
Mm-hmm.
So what you're saying that momentum of the ball is less than the momentum of the player, right? Right.
Yes.
Although the Velocity of the ball was higher as compared to the velocity of the player, right? Is that right?
Mm-hmm.
But momentum is less. So it is not direct only like when you calculate the momentum, it's not only velocity which will determine whose momentum will be higher, right? It's product
Yeah.
of mass and velocity both, right? Is that right?
Mm-hmm.
Okay. So when we do the product, then we see that oh, something is high, like the person is having higher momentum because the product of mass and his velocity is higher, right? Okay.
Mm-hmm.
Okay. Thus the momentum of the player is greater. Okay. Now, okay, what does it mean if something has a higher momentum? Like if I say that something has a higher momentum, then what does it mean? Do you know that?
Not sure.
Yeah, it is a more tendency to maintain that motion, right? Is that right?
Mm-hmm.
That is
Yes.
like it is a measure of that thing. Now, force and momentum are intimately related. Okay, yeah, that is by Newton's second law. Is that right? And do you know
Mm-hmm.
that by Newton's second law, rate of change of momentum is by rate of change of momentum is equals to the net force acting on it, right? It is not the force acting on it. It is the net force acting on it. Okay. Normally, what we see in our daily life, all these systems, most of the systems have constant mass. Their mass is not changing. Okay. So change in momentum is change in mass multiplied by velocity, right? So mass is
Mm-hmm.
constant, so we will take out mass outside, okay, here. And so it is actually mass multiplied by change in velocity, okay, that is momentum, okay. This is a special case when the mass is constant, okay. So F net by Newton's second law, net force acting on any object is rate of change of momentum. That means delta P by delta T. That means change in momentum by change in time taken, okay. So that is m times because the mass of the system is constant. So mass multiplied by delta V by delta T. And do you know what is delta V by delta T? That means rate of change of velocity with respect to time. What is that? Do you know this quantity? What is this?
Uh, which one?
Are you seeing the screen?
Yes. Wait, what? Wait, what? Like delta V over delta T?
Yeah. What is this? Is this acceleration?
Yes.
Yeah. So you can you write this like mass into acceleration, right? Okay. So this
Uh-huh.
is only true for our system which has constant mass. Okay. That is the thing. The systems for which the mass is not constant, you cannot say that change in momentum is equals to mass multiplied by delta V. Okay. Because mass will not come outside. Now, next after this, there is a question. Okay. This one. Can you read the question?
During the 2007 French Open, Venus Williams hit the fastest recorded serve in a Premier Women's match, reaching a speed of 58 meters per second. What is the average force exerted on the 0.057 kilogram tennis ball by Venus Williams' racket, assuming that the ball speed just after impact is 58 meters per second? That the initial horizontal component of the velocity before impact is neg- negligible, and that the ball remained in contact with the racket for 5 milliseconds.
Okay. So, how can you calculate the average force imparted on the tennis ball? Okay. So, can you find the change in momentum of the tennis ball? Hmm?
Um, wait, don't.
Okay. So, first tell me what is the initial momentum of the tennis ball?
0.057 times 58 meters per second.
Okay. So, this 58 meters per second is to the left side or right side? You can assume that this is to the right side. Okay.
Mm-hmm.
This is going to the right side. Okay. Now, after it has been hit by the racket, okay, what is the final momentum of the tennis ball?
Is it? Okay. Is it the same or no?
Let's check. I told you that momentum is a vector quantity, right? That is mass
Yes.
multiplied by velocity, right? It is not mass multiplied by speed. Is that correct? So,
Yes.
what is the initial velocity of this tennis ball? 58 meters per second in this direction. Is that right? What is the
Mm-hmm.
final velocity? Is that 58 meters per second in this direction? So can you
Yes.
write if you are considering this direction as positive, then would you consider this direction of velocity as negative 58 meters per second?
Yes.
Is
So,
that right?
oh, so wait, so it's zero, right? Initial
Yes.
moment.
Try to do this on your own.
What the, wait, what is it asking? What is
So
the
first tell
average?
me what is the initial momentum?
Uh, the 0.057 times positive 58.
Yes, times of 58. And what is the final momentum?
0.057 times negative 58.
Yes, that's correct. So that will give you the initial and final momentums, right? Okay. Now, after doing that, you will get the initial and final momentums, right? And what is the
Mm-hmm.
net force acting on any object? Is that rate of change of momentum with respect to time? That is delta P by delta T. Is that right?
Yes.
Is that right? So what is delta P? That means change in momentum, right? That is final
Uh-huh.
momentum minus initial momentum. Is that right? And delta T is the time. Remember, this is not the overall time. This is the time in which the momentum had changed. Are you getting that? In what time
Yes.
the momentum had changed? So, from the question, do you have the time in which the momentum was changing? That time in which the momentum was changing?
5 milliseconds?
Yes. So, you have in the denominator 5 milliseconds, 5 into 10 to the power minus 3. And what you have in the numerator? That is 0.057 multiplied by 58. Okay, so what is 0.057 multiplied by 58? Can you do the calculation, please?
3.306.
Okay, so the initial moment, so final momentum is negative of 3.306 and minus initial momentum. So initial is 3.306. Is that right? Is that
Yes.
right? So is this equals to negative of 2 times of 3.306 divided by 5 into 10 to the power minus 3. Sorry, this is minus 3. Erase this. Yes. So is that correct? Is
Yes.
that so? Is this equals to F net?
Yes.
Because that is rate of change of momentum with respect to time. So can you do this and tell me what is the net force acting on it?
Negative 1,322.4.
1322.4. Yes, that's correct. And the unit will be Newton. Is that right? Is that right?
Yes.
Now, what are they asking? Are they asking about just F net, the vector, or force?
Horizontal component?
So this is the horizontal component, right? Because the momentum is only changing in the horizontal direction, right? Is that right? Is that right?
Yes.
There is no initial vertical component of momentum, right? So no force also in
Yes.
the vertical direction, right? So this F net is actually the net force in the horizontal direction, right? Because we were only because there was only and only horizontal component of linear momentum. Okay. Now this net force is negative of 1322.4. That means what? what we had considered as the positive direction to the right, right? That means the force is acting in this direction, right? And that is of this magnitude 1322.4 Newton. Is that right? Is that right?
Yes.
So are we required to find the magnitude of the force or just the force?
Magnitude?
Okay. If they ask you to find the magnitude, so magnitude is you put an absolute sign on the net force, right? So absolute sign of
Mm-hmm.
this 1322.4. So this will become magnitude, right? So 1322.4 newtons. Is that okay? Is that making sense?
Yes.
Okay, perfect. Uh, but what is the average force imparted here? Okay. Assuming the speed is just after 58 meters per second. Oh, was the initial speed also 58 meters per second?
Wait. No.
The initial speed was zero, right? Is that right?
Yes.
That the ball was stationary. So we have to just modify one thing. The final momentum is this, and there is no initial momentum, right? That is zero. Is that right? So we'll divide this
Yes.
answer by two, right? Is that right? We will
Mm-hmm.
remove this two here. So you will get this as divided by two, divided by two. So what you will get is answer divided by two. That is
Uh,
661.
s-
661 newtons. Okay. 661 newtons. Is that making sense?
yes.
Okay, perfect. So that is the net force acting on. And if in the question it was given that the initial speed was 58 meters per second, and after hit by the racket, it has the same speed but in the opposite direction, then we will use this approach of solving. Is that right?
Mm.
Okay.
Yes.
Okay. Now, what is impulse?
Change in momentum.
Yeah, yeah. By formula wise, impulse is actually change in momentum. Okay. So there are this. See, this is impulse. The impulse is also equals to change in momentum. Sometimes you can also calculate an impulse like this: F net multiplied by delta t. So F net is the net amount of force that has been acted for the given short interval of time. Okay, for the given short interval of time. Is that making sense?
Yes.
Okay. So sometimes what they will give, the force is variable. The force which is acting, that is variable, and that is being applied for a given time. Okay, for the given time. Okay, let's say
Mm-hmm.
up to this time. So do you know what does area under the graph gives? Area under the graph gives a quantity that is product of the y-axis quantity and the x-axis quantity. Is that right? That is F
Yes.
multiplied by delta. So will that give the impulse? Is that right? Is that
Mm-hmm.
right? So area under a force versus time graph gives the impulse. Okay. So sometimes they can give you the F net and delta t. Sometimes they will give you the initial momentum and final momentum. Okay. So to find the impulse, you can either use this formula or this one formula. Okay. There are two formulas. Okay.
Mm-hmm.
Okay. So this quantity F net multiplied by delta t, that is the time of over which this net force is acting, that is called impulse. Okay. Okay. So for solving some questions of impulse, okay, let's do this question. Calculate the magnitude of the impulse, two billiard balls. Okay. So two identical billiard balls strike a rigid wall with the same speed. Okay. So they have the same speed and are reflected without any change in speed. So speed is not changing. Okay. The first ball strikes perpendicular to the wall. So this is the wall. So the first ball strikes perpendicular to the ball. Okay. Is that okay?
Mm-hmm. Yes.
And what is happening with the second ball? The second ball strikes the wall at an angle of 30 degree from the perpendicular. Okay. So let's say this is the perpendicular. So it strikes at an angle of 30 degree with the perpendicular, right? So like this. Is that right?
Yes.
Is that right? And then what happens? And bounces off at an angle of 30 degree to the perpendicular. That means it bounces off back at the same angle, right? That is 30 degree. Is that right?
Mm-hmm.
Is that right? Okay. So this is for the second ball. Let's say this is the second ball. And this is the first ball. This is the ball one. This is the ball two. Okay. Now, what is happening? The first ball strikes the wall. The second ball. Okay. So when the first ball will strike perpendicular, it will come back in the same direction. Okay. Now bounces off at an angle. Okay. So determine the uh, direction of force on the wall due to each ball. Okay. Now we have to first find the momentum and change in momentum. Okay. So they are having the same speed. Is that right? Is that right? They are having the
Yes.
same speed. Okay. Okay. They are having the same speed. Right. After bouncing back also they have the same speed. Right. Is that right?
Mm-hmm.
But their directions of velocity are changing. Right. Is that right?
Yes.
Let's say their speed is v meters per second. Okay. Okay. So for the ball one, what is the initial momentum? Let's say mass of the ball is m. Okay. So if we consider this direction as positive and the opposite direction as the negative. Okay. So initial momentum of the ball one is that mass multiplied by v. Is that right? Is that
Yes.
right? And what is the final momentum of this ball? Is that
Mass multiplied by negative v.
yes? That means negative of m times of v. Is that right? Okay. So
Yes.
what is the change in momentum of the ball? So final momentum minus of initial momentum. Is that right? So that means of
Yes.
negative of 2 times of mv. Right? Is that right?
Mm-hmm.
And the ball strikes the ball. Okay. Okay. So uh, the net force acting on the ball is equals to rate of change of momentum, right? Delta p by delta t. Is that right? So
Yes.
negative of 2 mv by delta t. Is that right? Is that right?
Yes.
So this is the net force acting on the ball. Is that right? And
Yes.
the sign is negative, right? So then the sign is
Mm-hmm.
negative. So net force acting on the ball is in this direction. Is that right? Is that right?
Yes.
Is that right? Okay. So by Newton's third law, when the ball was just striking the wall, when it just struck the wall, okay? Let's say it was here. Okay? So the so the wall has imparted a force on this on this ball, right? In this direction. Is that right?
Mm-hmm.
Is that right? So by Newton's third law, what will be the direction of the force applied by the ball on the wall? By
Can I
Newton's
say that
third
again?
law. Okay. So if this ball, there's a wall, okay? Wall is applying force on this ball that is in this
Yeah.
direction, right? This we calculated and we got F net on the ball in this direction. And this force is applied by the wall on the ball. Is that right? Is that right?
Yes.
Now, when the wall is imparting force on the ball, then at the same time, the ball will also impart a force on the wall. Is that right? Because of third
Yes.
law? Is that right?
Mm-hmm. Mm-hmm.
So what will be the direction of that force? That ball will impart on the wall. Will that be of same magnitude and opposite in direction? Is that right?
Yes.
By Newton's third law. So on
Yes.
the ball will apply in this direction, right? And that is what they are asking in question number A. Is that right? Determine the direction of force on the wall due to each ball. So due to the the first ball will impart force on the wall in this direction. Is that right? That means to the right
Mm-hmm.
side. Is that right? Is
Yes.
that making sense? Okay. So in man equations, and will this magnitude will be same as the magnitude of the F net? Is that right? By third law,
Yes.
right? Okay. Now, let's do the same thing for question for the second ball. So what is happening for the second ball? So second ball is striking like this. Is that right? It is bouncing back like this. Is that right?
Yes.
Is that right? So what is the initial momentum? So this momentum has two components. Is that right? One is the vertical component and one is the horizontal component. Is that right? Why?
Yes.
Because this velocity has two components. One the vertical component of velocity and one the horizontal component of velocity. Is that right?
Yes.
Is that right? Okay. So what is the horizontal component of momentum? Initial momentum.
Positive.
Or if you don't want to calculate the horizontal component of initial momentum, what you need to do, this is a vector, right? Momentum is a vector. So what is the initial momentum? So initial momentum is pi, is mass multiplied by velocity. Okay. And what is the direction of this? The direction of this momentum is like this. Is that right? Is that
Yes.
is that right? Let's say this is some theta. Yeah, this theta is what? This is 30 degree, right? So this is also 30
Uh,
degree. Right? So this is 30 degree. Right? Is that right? And what is the
yes.
final momentum? So the final momentum is like this. So that is in this direction. Is that right? So this final
Yes.
momentum is in this direction. What is the direction of the final momentum? This is
Negative.
you can just do this using the concept of vectors. Okay, uh, that will make the things more easy. See, if this is the final moment, right? Is that right? So this is making an
Mm-hmm.
angle of 30 degree with this. Is that right? And what was the initial
Yes.
moment? The initial momentum was in this manner
Um.
here, right? Is that right?
Mm-hmm.
Is that right? It was making an angle 30 degree with this. Now, what is
Yes.
PF minus PI, right? So PF minus PI, that means you will add PF plus negative of PI. Is that right? Is that right?
Uh-huh.
Is that right? So what is negative of PI? So negative of PI is this a vector like this? Right. We'll extend this in this direction. Is this vector called negative of PI vector?
Yeah.
Is that right? Of same magnitude and opposite direction to the PI? Is that right? So,
Uh-huh.
yeah. Can you ask your question? Hello.
No, no.
So this is negative of pi vector. So pf minus pi is actually pf plus negative of pi. So you will add these two vectors, right? Right. They have the
Mm-hmm.
same magnitude. Their magnitude is m multiplied by v, right? So their magnitude is
Yes.
same. Just they are at different angles, right? So this is at 30 degree. So this is also at 30 degree. Is that right? Is that right? Will their
Uh-huh.
vertical component of the momentums will cancel each other when you add both of them? Will their vertical components this direction will they cancel each other
Um.
because they are PMV
Yes.
of sine 30 and MV of sine 30, right? They will cancel each other. So the net will be in the horizontal direction, right? So the horizontal components will be they will be negative of MV cos of 30 degree, right? Plus negative of MV cos of 30 degree. Is that right? Is that right?
Yes.
So they are both in the same directions, right? So you will add
Mm-hmm.
both of them. Is that right? So the net momentum, net rate of change of net change in momentum will be equals to negative of 2 mv cosine of 30 degree. Is that right? Is that right?
Yes.
Its direction is like this. Is that right?
Mm-hmm.
Is that right? Is that right? So,
Yes.
so this is the rate of change of, this is the change in momentum, right? And F net on the ball is delta P by delta T. Is that right? So
Mm-hmm.
the sign of delta P will give you the sign, will give you the direction of net force acting on the ball. Is that right? So the sign, so what is the direction of delta P? That is in this direction. Is that right? That means
Yes.
the net force acting on the ball will be in this direction. Is that right? Now the ball was in contact with the wall here, right? And the net force imparted on the ball is in this direction. We have calculated that right now, right? By finding the sign
Yes.
of delta P. Is that right? So
Uh-huh.
if the wall is imparting force in this direction on the ball, then ball will impart force on the ball in which direction? Will that be in this direction? Is that
Uh,
by Newton's
yes.
third? Right. So for both of the cases, the force on the wall by the balls will be in this direction to the right side. Is that right?
Yes.
So that is the thing. So now I am just going to the theories instead of doing a lot of questions. Okay. Because you already have some questions, right?
Yeah. Also, wait, can we go over inelastic and elastic collisions? Like just
Yeah, sure, sure. Before going there, I would like to check that. Do you know this that when you apply collision, like law of conservation of momentum? Okay. So when you can apply, do you know what is law of conservation of momentum?
delta P. Wait. No, wait, I don't remember.
Okay. This says that when the net force in the selected system, okay. So before going to law of conservation of linear momentum, I would like to tell you the definition of system. What is system? What is internal force? And what is external force? Do you know about this? Hmm?
Uh, I believe so.
Okay. So what is system? Like you can select system anything, whatever you want. Okay. Whatever you want, you can select as a system. You can select the car one only as the system, or you can select the car two only as the system, or you can select both of the cars of the as the system. Okay. Now the force which is imparted by one part of the system on the another part of the same system, that is internal force. Okay. And what is
Yes.
external force? It is it is the force imparted by something which is not part of the system on the system. Okay. Okay. That's why we have
Yeah.
selected a system. In this case, we have selected this two cars as one system. Okay. Okay. Car one
Mm-hmm.
and car two. So when the two cars collide, okay, then the car one exerts a force on car two, right? And car two will
Yes.
also exert a force on car one, okay, by Newton's third law, right? So that force which car one is imparting on car two and car two is imparting on car one, that becomes internal force when you select both of the car as one system. Are you getting that?
Yes.
Because they are applied by one part of the system or the other. But if you only select this car as the system, okay, if you only select this car as the system, then during the collision, will there be any external force acting on it or not?
Wait, say that again?
If we select only car 1 as the system, okay, if we select only the car 1 as the system, and when this car will collide with the car 2, okay, car 2,
Yes.
then will there be any external force acting on this system when both of them
Car
will
two.
collide? Hmm?
Car two is external force.
Car 2 is not external force, the force applied by car 2 when both of them
Oh,
will collide, okay, when both of them will
okay.
collide, okay, then
Okay.
this is car 2 and this is car 1, okay. Thus, this car 2 will apply a force on this in this direction. Is that right? on the car 1.
Yes.
And similarly, car 1 will also apply a force on car 2 in this direction. Okay. So this F1 is applied by car 2 on car 1. Okay. So if you select only this car 1 as the part as one system, so is there any external force acting on it during the collision?
The force of car 2 and car 1.
Yes, yes, that is external force, right? Because
Yeah.
now your system is only car 1, right? So any force that is applied by car 2, it comes will become an external force, right? But if you consider both of the cars as part of one system, right? Then the force applied
Uh-huh.
by car 2 on car 1 or the force applied by car 1 on car 2, both of these forces will become internal, right? Is that right?
Yes.
F1 and F2 are internal. Is that right? Is that right?
Yes.
But in this scenario, F1 was not internal, F1 is external, right? Because you have selected a system that is car 1 only, right? In the first case. So, what is external force and what is internal force? That depends upon the system you have chosen. Okay. Now, you got to know about internal force, external force, and system, right? Now, in all the questions of law of conservation of momentum, you have to be smart in choosing the system. Why? Because law of conservation of linear momentum says that, what does it say? It says that when the net external force on the system is zero, right? Okay, then 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 what happens? Then momentum is conserved. Okay, when the net external force is zero. So a system, there is a system. Okay, a system
Mm.
in which there is a net external force. Okay, net external force. Remember, I am talking about net external force. It is not external force. Okay? So net
Okay.
external is zero. That system is called isolated system. Okay. Okay. So we have to
Yep.
find systems which are oscillated. Okay. Okay. And in that system, the momentum is conserved. That is, initial momentum is equals to final momentum. Also, that is true for a particular direction, right? Let's say
Mm-hmm.
this system. Okay. So net force, if we say that net force, net external force, okay, is zero on this system, right? So momentum is conserved. That means initial momentum of the system is equals to final momentum of the system, right? But in some scenarios, what happens? This is the system, right? And the net external force along x-axis is only zero, only along x-axis, right? If that is only net external force along x-axis is only zero, so momentum along x-axis will be conserved. That means momentum along x-axis will be equals to initial momentum along x-axis will be equal to final momentum along x-axis, right? And if there is only net force along y-axis, okay, net external force along y-axis is zero, then initial momentum along y-axis will be equals to final momentum along y-axis. But if in this system net external force is zero, it is given that it is not x or y, right? It is the net
Uh-huh.
external force is zero, right? Then you will apply both of the linear momentum equations. That is pix is equals to pfx, piy is equals to pfy. Okay. Or you can also apply like this: pi is equals to pf. Okay. Are you getting that?
Yes.
Okay. So we have to just select the systems which are isolated system. That means in which the net external force on the system is zero. So after, okay, so this is an example. Like, would you like to see this example, or would you like to go on collisions?
Collisions.
Okay, perfect. Because I think you know these things, right? Okay,
Yes.
okay. So collisions are of two type. Okay, what are they? They are
A
elastic
lot.
collision and inelastic collision. Have you done this till now, or like should we
We
just?
have like we have like two more. We have like totally inelastic and like I think partially inelastic or explosions or something like that.
Yes, yes, we'll go there. There are something
Okay.
like which are between them, right? One is completely elastic, one is completely inelastic, right? And there is something
Yes.
between them which is partially elastic or partially inelastic, right? Is that right?
Uh-huh.
Okay. So that is, we'll discuss that. Okay. First, let's discuss about elastic. What happens in elastic collision? First thing, in all kind of collisions, okay, momentum is conserved of the system, right? Okay.
Yes.
Is conserved in all the collisions. Either it is elastic or inelastic, right? Momentum is
Mm-hmm.
conserved, right? Linear momentum is conserved in all of them, right? Okay. Now, the thing is that now what is not conserved and what is conserved in elastic and inelastic, like that is the kinetic energy. Okay. Kinetic energy. Okay. Kinetic energy is conserved in the elastic collision. Okay. Is that making sense?
Yes.
And
Yes.
kinetic energy is not conserved, is not conserved in the inelastic collisions. Okay. In inelastic collisions, what happens is that either the initial kinetic energy is lost in the form of friction or some kind of non-conservative work, okay, by the non-conservative force,
Mm.
okay, heat, friction, or anything, right? Or also in some cases, kinetic energy increases in cases of inelastic collision, right? So in inelastic collision, kinetic energy can increase or decrease. Okay. Mostly in most of the cases, the kinetic energy decreases, right? In some few
Mm-hmm.
cases, the kinetic energy increases. That means kinetic energy is not conserved. That means the initial kinetic energy is not equals to final kinetic energy in this case, right? And in this case, elastic collision, initial kinetic energy is equals to final kinetic energy. Okay. That is the essence. So while solving these problems, you have to write two equations. One is the momentum conservation equation and then the kinetic energy equation for the elastic collisions, right? That can help you solve many problems. Now, that was about kinetic energies. So an elastic collision is one that also conserves internal kinetic energy. Okay. And what is internal kinetic energy? Internal kinetic energy is the sum of kinetic energy of the objects in the system. Okay. Sum of
Mm-hmm.
kinetic energy of all the objects in the system. Okay. Let's say the system has two cars, car 1 and car 2. Okay. Car 1 and car 2. Okay. So, what is the initial kinetic
Yes.
energy of the system? That will be 1 by 2 m1 v1 square plus 1 by 2 m2 v2 square. Right. This is the internal kinetic energy of the system. Okay. And if there are two systems like this, so what is the momentum of the system? It will be m1 v1 plus m2 v2, right? Right. This
Yes.
is the vector addition of the two two momentums. Okay. That is the momentum of the system. Okay. Because when you have two bodies in the system, right, then you will add the two the of the momentums of the two, and also you will add the kinetic energy of the both, right? Then you will get the
Mm-hmm.
total internal kinetic energy. Now, in this system, right, the surface, if in this system, the surface was not frictionless, right? If the surface was not frictionless, right, then do you think that could you apply law of conservation of momentum here?
Um. Wait. Which one?
Are you seeing this screen? If the surface
Yes.
was if the surface was not frictionless,
There would be a loss, right?
yeah, if the surface was not frictionless, then what would happen? The blocks will collide, right? But there will be force acting on the two blocks, right? Because of the friction, right? Is that right?
Yes.
So that will become the external force. And so the momentum will also not conserved in this case, right? Because
Yes.
there is some external force, friction acting, right? So in all most of the momentum problems, you will be given that the surface is frictionless, right? So that the net external force, when you select both of the masses as the system, then the net external force on the system will be zero. Is that right? So you can apply.
Yes.
So you can consider that these two masses as a system which is isolated system, right? Because net external force will be zero in this, right? And
Uh-huh.
Yes. What you're saying?
Yes.
Are you getting that?
Uh, yes.
Okay. And if kinetic energy initial is equals to final kinetic energy, then the system you have selected, that is a and the system we have selected, and that has undergone collision, right? So the collision is elastic collision. Okay. Is that making
Mm-hmm.
sense?
Yes.
So see you how they are doing. While writing this equation, remember it is mass multiplied by velocity, not mass multiplied by speed. Okay. So the sign of the velocity will matter a lot. Okay. Okay.
Mm-hmm.
Okay.
Yes.
Can you try this one question, or like should we move to questions which are in your modules? So we try that.
Yes.
Okay, perfect. Uh, what was it? I think question number 5 you can do easily, right? That's a simple thing.
Yeah. Wait,
Which
are
question
these?
you did that?
I can. Yeah, I could do 5 easily.
Okay. Question number 6. A 60 kg woman jumps from the burning building and falls 10 meter before making contact with a safety net, which stops her in 0.12 seconds. Okay. So can you tell me what is the average force exerted by the net on her?
Uh,
So
delta.
the force that has been
Delta.
acted on her, will that be related to change in momentum of her? Is that right?
Yes.
Is that right? And that change in momentum has happened in what time? That is also very important, right? That will decide the amount of force that is acting on it. Is that right?
Yes.
So what is the initial velocity in this case?
Uh, Wait. Would it be? Wait.
So
Would
wait.
this be VF? Would this
Yes.
be VF equals
Yes.
VO plus 2?
Wait, listen to me. Actually, what you are calculating the average force. Is that right? Is that right?
Yes.
So how we were calculating the average force? Let me show you that.
Uh,
That
Delta P over
was
delta T.
delta P over delta T, right? That was PF minus PI by delta T, right? So in this
Mm-hmm.
equation, this PF and PI and delta T, what is that? When the momentum was changing from PI to PF, right? Is that right?
Yes.
In the given time delta T, then force acting was F net. Is that right?
Yes.
Right? So delta T is the time in which the momentum is changing from PI to PF. Is that right? Is that right?
Yes.
So if the time in which the momentum is changing from Pi to Pf is more, then the net force will be acting on it will be more, right?
Uh-huh.
So in what time is the momentum changing? So the momentum is changing in what time? That is 0.12 seconds. Is that right? Is that
Uh-huh.
right? Is that right? And the momentum is changing from what to what? In 0.12 seconds, from where and where is the momentum changing? Like what is the initial momentum and what is the final momentum that is happening in this 0.12 seconds? So if you don't know the momentum, right, and momentum is mass multiplied by velocity, right? Mass multiplied by final velocity. Is that right? So
Yes.
in this 0.12 seconds, right, what was the initial moment, what was the initial velocity and what is the final velocity? First tell me what is the final velocity after 0.12 seconds.
0.
Zero, right? So that is mass multiplied by zero. So the final momentum comes out to be zero. Is that right? Is that
Uh-huh.
right? And what is the initial momentum? That means when the change has just started, right? Is that right?
Yes.
That means when the person just landed over the net, right? He was just about to touch the net. Is that right? So what
Yes.
was his velocity at that time? Can you tell me that? So how would you
Would
find that velocity? He had jumped from here, right? Is that right?
Yeah.
There is this net. Okay. There is this net. Right. She had just came here. So she started from here. She traveled a vertical distance of what? 10 meters, right? Is the
Mm-hmm.
acceleration due to gravity is 9.8 meters per second square? Is that right?
Yes.
Is that right?
Yes.
So, what is the velocity? And when she had just jumped off the cliff, this time here initial velocity would be 0, right? So she would have some velocity here, right? Is that right? So how would
Mm-hmm.
you find the final velocity when the acceleration is given, that is negative of 9.81, when the displacement is given, that is negative 10 meters? Is that right? And uh, and what else is given? Is there anything else given? Yes. Initial velocity is 0, right? That means just before jump.
Final velocity, you mean?
Yes, final velocity. Just when it strikes the net. So will that be given by Vf square is equals to Vi square plus 2 times of A times of delta Y by this equation of motion? Is that right?
Yes.
Because this is a constant accelerated motion, right? This is a case of free fall. So the final velocity when it has just strike the net is Vf square is equals to 0 square plus 2 times of A, that is negative of 9.81, multiplied by delta Y, that is negative of 10. So Vf is equals to square root of 20 times of 9.81, right? 20
Mm-hmm.
times of 9.81. So what is this? Let's calculate this. 20 into 9.81 and square root of 196.2. So we got 14, right? So Vf is equals to 14.01 meters per second. Okay? And this is the downward direction. Is that right? This is the
Mm-hmm.
direction. Is that right? So
Yes.
just before hitting, it has 14.01 meters per second in the downward direction, right? So what is the momentum because of this? So can you write it like this also? Downward direction velocity as negative of 14.01 meters per second. Is that right? So what
Yes.
is the initial momentum? So initial momentum is this. This is the initial velocity. If you are considering the case when the momentum is changing, then this final velocity is actually the initial velocity. Is that right? Is that right?
Yes.
Is that right? So that is mass. What is the mass of this woman? That is 60 kgs, right?
67.
Multiplied by negative of 14.01. Is that right? Mass multiplied by velocity. Okay. So that comes out to be 840.4. Is that right?
Mm-hmm.
Negative of 840.4 kg meters per second. So this is the initial momentum, right? Is that right? And
Yes.
final
Yes.
momentum was 0, right? After
Yes.
in that 0 point, what is the time? In that 0.12 seconds, right? So the momentum
Mm-hmm.
is from negative of 840.4 to 0, right? In what time? The time is 0.120 seconds, right? So what is the net force acting on the woman? That is the change in momentum of the woman divided by the time in which this momentum is changing, right? So change in momentum is final minus of initial, that is minus of minus 840.4. Is that right? Divided by
Yes.
0.12. Is that right? So this will come out to be 840.4 divided by 0.12. Okay. So you will get your answer as 7003.6. Okay. So that is the net force acting. This is the net force exerted on the woman. Is that making sense or not? Tell me.
Yes.
Is that making sense? Hmm?
Yes. Yes.
Okay. Now, another question. Now tell me what after this?
Oh, wait, which one?
We have done question number 8, right? Now, which
Yes.
question would you like to practice after this? Question number 18?
Uh, I think I already did 18. 22.
Okay, 20. Question number 22. Try to solve this first yourself and tell me your approach, what you will do. So first write down what things are given, right? So what are given? What is given in the question?
Mass
So let's
of
write
the
mass is
person.
equals to 65 kg, right? What else is given?
The mass of the snowball.
Okay. So this is the mass of the ocean, mass of the snowball, that is 0.0450. Okay. Forward with the count, the speed of it. So, so the snowball is moving, right? So we will also draw a visual representation of what is happening, right? Is that right?
Mm-hmm.
That will help you better solve physics questions, right? So, so actually, the snowball is thrown, right? Is that right?
Mm-hmm. Yes.
So a 65 kg person throws a 0.045 kg snowball forward with a ground speed of 30 meters per second, right? That means 30 meters
Mm-hmm.
per second, it is thrown like this. Is that right? A
Yes.
second person with a mass of 60 kg catches the snowball, right? Right. So there is
Yes.
a second person. So the first person is here who is throwing this snowball. Okay. Oh, the snowball looks much bigger than the man, right? Okay. And the second person is here who is catching, who is trying to catch, right? Who is trying to catch that snowball, right? Both
Uh-huh.
people are on skates, right? So they are on skates, right? Is that right? Hmm.
Yes.
The first person is initially moving forward with a speed of 2.5 meters per second. Okay. So initially it was moving with a speed of 2.5 meters per second in the forward direction, right? What are the
Uh-huh.
velocities of the two people? Two people after the snowball is exchanged. Okay, let's check that. So first consider the first ball, first man and the ball as the system. Okay. If you consider this as the system, okay. So when this bomb person throws the snowball, okay, okay, and when it was not throwing the snowball, was there any external force acting on it?
No.
No, right? There is external forces are acting that are gravity and normal, right? But there is no
Yes.
net external because they are canceling each other. Is that right? So there is no net
Uh-huh.
external. External forces are acting, but net external force is not there, right? That is zero. Is that right?
Yes.
Is that right? Okay. So net external force is zero on this system. So this system is isolated system, right? So you can apply law of conservation of linear momentum in this system. Is that right? So this system has
Yeah.
two things, right? The person and the snowball. Is that right? Right.
Yes.
Initially, the snowball is in the hand of the person, right? He has not thrown it. Is that right? Is that right?
Mm-hmm.
And in the final situation, he has thrown the snowball. Is that right?
Yes.
Is that right? So initially, uh, the momentum of the system, what is that? Is that momentum of the man plus plus momentum of the snowball. Is that right?
Yes.
Is that right? Okay. So what is that? Let's see that. So initially the person is moving with 2.5 meters per second in the forward direction, and there is a snowball in his hand, right? Is there a snowball
Uh-huh.
in his hand?
Yes.
Okay. So if that snowball is in his hand, right? So what is the mass of the person? That is 60 kg, right? 65 kg. So 65 kg multiplied by 2.5 meters per second. Is that right? And the snowball that is of mass of 0.045 kg. Is that right? Is that right?
Uh-huh.
And that is also moving at 2.5 meters per second because that is on the hand of the person. Is that right?
Yes.
Is that right? So this is the initial momentum of the system. And what is the final momentum of the system? Now in the final system, what is happening is that now the man is moving with a that 65 kg man, that is moving with a speed of what? What is the speed of the man? We don't know, right? Is that right?
Yeah.
We don't know what is the final speed of the man. That is v. Okay. Okay. And
Uh-huh.
what is the speed of the snowball? What is the final speed of the
Oh,
snow?
0.
Please read the question. Is that zero? Check that.
Wait, wait, is it 0? Wait, hold on. No, wait, no.
So snowball
It's
forward with a
30.
ground
It's
speed
30.
of 30, right? Yes. So it's 30, right? So now the
Uh-huh.
final speed of the ball is 0.045 multiplied by 30. Is that right? Is that right?
Uh-huh.
So when you consider the system as snowball and the man, right? So this is the final momentum of that system. Is that right? Now, since there is
Yes.
no external force acting on the system, so and this is an isolated system, right? So the momentum will be conserved. So the initial momentum will be equals to final momentum. Is that right? Is that right?
Yes.
We will equate both of them, both of this, and you will find the final velocity. Is that right? Of the man.
Yes.
Is that right?
Uh-huh.
What after that? So you will get the final velocity of the man, right? Now, how would you find the what are the velocities of the two people after the snow is exchanged, right? Okay. Okay. Now the second person is at rest. Is that right? Is that right? He is on the
Yes.
skater board, right? So his initial momentum is what is the initial momentum of the second person? Is that zero? Because
Yes.
this was at
Wait,
rest.
no. I wait. The first person. Oh, wait, no, he's at rest. Yeah.
Oh, wait a minute. So what you are considering as the system in the second case? Now in the second case, you are interacting the ball, the snowball, right? This is snowball and
Uh-huh.
the man. Is that right? So would you consider both of them as the system?
Yes.
Snowball and the man. Because if you consider only the man as the system, then when he catches the ball, then the ball will exert force on it, right? And that will become external force, right? Is that right?
Uh-huh.
So you have to consider the snowball and the second man as the system, right? The second man as the system, right? Is that right?
Yes.
So if you consider both of them as the system now, so what is the initial momentum of the system?
0.
Okay. So what does the system consist of? Snowball and the second man. Is that right? In the second case. Is that
Yes.
so? What is the momentum of the man? Initial momentum of the man? Is that
Uh, of the man is 0, right? Because he has 0
and
velocity. He's at
yes,
rest.
yes. And the moment and the system consists of snowball and man both, right? So what is the initial momentum of the man of the snowball?
0.045 times 30.
So what is the initial momentum of the system? That is 0 plus 0.045 multiplied by 30. Is that right? So this is the initial
Yes.
momentum of the system. The initial momentum of the system is not zero, right? It is 30 multiplied by 0.045. Is that right?
Uh-huh.
Is that, is that right? Now, final momentum. Now, final momentum when the ball is being like the second person catches the ball, right? So when the second person catches the ball, now both of them will attain a same velocity, right? Because he has catched this ball and the ball is now in his hand, right? Okay,
Uh-huh.
the ball is now in his hand, right? So now both of
Yeah.
them will move with the same velocity in this direction, right? We don't know the direction, that's it. Okay, so now the both of them will move up with the same velocity. Now what is the final momentum of the system? So mass of the snow multiplied by velocity of the snow plus mass of the second man multiplied by velocity of the second man. And will the velocity of the second man and the velocity of the ball be same in the final
Yes.
case? Right. So this can be written as ms plus m2 multiplied by v. Is that right? And what is the mass
Yes.
of the second person? That is 60 kg, right? So 0.045 plus 60 kg multiplied by v. So this is the final momentum of that system, right? And you will equate this final momentum to the initial momentum you got here. Is that right? And by
Yes.
this, you will get the final velocity of the second person. Is that correct? So we have
Yes.
seen, we have selected two systems. In the first system, we have considered the first person and snowball. And in the second scenario, we have considered the second system as the snowball and the second person. Is that right?
Yes.
Is that right? Why we have considered the snowball and person as the systems in both the scenarios? Because if we consider that, then the force by the ball on the man and by the man on the ball becomes internal forces, right? Right. So no
Mm-hmm.
external force is active there, right? And you can apply law of conservation of linear moment. Is that right? Is that making
Yes.
sense? Okay.
Yes.
So that's all. So you can solve more questions on this. Is the concepts clear for now?
Yes.
Okay. So try to solve more questions on this. Okay. Momentum conservation is a very good concept. Okay. There are some, they have some missing graphical questions. Oh, they have some graphical questions. Okay. So in today's class, we have given a lot of time to the theory. Okay. In next class, what we'll do, we'll practice more questions. Okay.
Okay.
Okay. Okay. Perfect. Okay, then bye
All
bye.
right.
And one more thing. Okay, the thing is that don't like I will recommend you what to do. Like if you are doing the classes, right? So if you have taken one class now, right? So try to take the class, another class on the next day or day after. Okay, because if you give a lot of gap between the classes, right? Then you will forget the things which I am teaching in the class. Are you getting that? Are you
Yes.
getting? That's why don't create a big gap between the classes. Okay.
Okay. Okay.
Okay then. Bye bye. Take care.
All right. Thank you. Thank you. Bye bye.
Yeah, welcome.